So hello everyone and welcome back to SWEcodes. So this video is in continuation with the binary search series, and we have a new problem here, that is square root of x. So let's read this problem once. So what this problem says is, like, we have a given a non-negative integer x and we have to return the square root of x rounded down to nearest integer, and the return integer should be non-negative as well. And what we have to do is, like, we don't have to use the built-in functions, the for or the this method in Python to calculate the square root, or we cannot use the math.square root x in Java or C++. So what you have to do is, like, you have to find the square root of an integer, and it should be rounded out down to nearest integer. Suppose for 4, since it is a perfect square, 2 into 2 is equals to 4, the square root of 4 is 2. Otherwise for 8, if you will calculate the square root, it should be 2.82842, something like that, and it should be rounded down to the nearest integer. Rounded down means if we will round this to the greatest integer, then it should be 3, but what we need is, like, we need to round it down to the nearest integer. So what we need is the integer whose square is less than equals to 8. If we'll keep 3, if we'll round it to 3, then 3 square would be 9, and that would be greater than 8. So rounding down to the nearest integer means we need the integer value whose square is less than equals to 8. Yeah. So quickly understand the solution. Let's try to visualize the solution. Suppose we have our number we have our number as 8 and we want to find its square root. And how can we apply binary search technique here? So what could be our search space? So suppose our search space should start from 1, because 0 square is 0, so we cannot take 0. So for 0 we can check, like, if n equals to 0, we can directly return 0, but for others numbers we'll have to find a search space to apply binary search. So what could be the search space? If you think carefully, the search space should start from 1 and should not go beyond 8. Actually it should not go beyond square root of 8, because square root of 8 into square root of 8 will give me 8. But we don't know the square root and we don't have to use built-in function. That is why we are applying binary search. So how we can apply binary search here is very simple. Like, if I initialize my search space from 1, let's go like 1 2 3 4 5 6 7 8. So what I told is, like, so square root of x, what is the condition? So condition is x square should be less than equals to 8, and we want to find the maximum value that satisfies this condition. Why I have written this this condition? Because we want to round it down to nearest integer. That is why I put x square less than equals to 8. So if we'll see here, 1 square equals to 1, that is less than equals to 8, yeah, it's true. 2 square equals to 4, that is less than equals to 8, it's true. 3 square equals to 9, that is less than equals to 8, it is false. So we don't have to check for 3, the answer would be 2. It is the maximum value satisfying this condition. So if, suppose, write this condition as f of x and try to write the true or false value. So for 1 it will be true, for 2 it will be true, and for all this it will be false. Yeah. So with our technique, what we can get? With our technique, I told you what we can get is, like, we can get the first value, we can get the transition point, the first value for which the condition satisfies or not satisfy. And if we get the first false value, then we know that the previous element should be the last true value. So let's revert this condition something like this. Since f of x is x square less than equals to 8, suppose define g of x as opposite of f of x. That means also x square greater than 8. Since it is less than equals to then the opposite would be greater than 8. And now define the true and false values for g of x. So this will give false, this will give false, and here on we'll have true values. So if we'll see carefully, if we can find the first true value, then we know that our answer is the last false value from g of x, because this last false value is corresponding to the last true value that satisfy this condition, x square less than equals to 8. So what we want to find is like this transition point, this transition point. So we can find from here directly, instead of checking for true, we'll check for false. But I have just done a simple thing. I have just reverted the function, like created new function g of x that is opposite of f of x, so that we have our similarities with the other problems. We have similarities with the other problems. So if we will revert this condition, x square less than equals to 8, then your condition becomes x square greater than 8. It's not equals to here. It is not equals to here. It's x square greater than 8 only. Okay. So with our technique, we guarantee that we can find the first true value. It's guaranteed. We can find the first true value. And if we get the first true value, then we can guarantee that the previous element would be the maximum false value, and this would be the our answer. So it's very simple. Let's try to implement it. Like int low equals to will keep as 1, and what could be the input range, we can check. Input could be 0 also. So for 0 will directly return 0. If x equals to 0 will return 0, and let's define our high value to x. You see, this is our search space. This is our search space. Then we know that we are running a while loop from low to less than high, and we are calculating a mid equals to low plus high minus low by 2, something like this. Yeah. What is our condition? What was our condition? The condition was x square less than equals to 8, and we want to revert that condition to have the true value. So after reverting, so actual condition was something like this: x square x into x should be less than equals to 8, and we have to return this, revert this. Yeah, we have to revert this. So this will give us the first true value satisfying, not satisfying this condition. So the previous element would be the last values or the maximum value satisfying this condition. It's very simple. So instead of writing it as not x square less than equals to 8, I can write it as x square greater than, mid square greater than x value. Yeah. So what we have to do, high equals to mid here, else what we have to do is low equals to mid plus 1. Yeah, at the end we'll have the low, and low is the first true satisfying this condition. Like the condition is f of k equals to k square greater than x. I'll just do this, k square greater than x. So what could be your answer? Your answer should be low minus 1, because low minus 1 will be the maximum value not satisfying this condition. That means low minus 1 is square must be less than equals to 8. So that should be our square root. Let's try to run it. Yeah, it's accepted. Now let's try to submit it. So we got our wrong answer for 1. Oh, 1 what we got, okay. So for 1 also, since we are doing minus 1 here, for 1 also we can check if it's then equals to 1. If it's 0 or 1, then we will return that number itself. So if x equals to 0 or x equals to 1, will return that number itself. Yep. Now try to submit it. So yeah, if you will see, this mid square is causing the overflow, cannot be represented in type int. Okay, yeah. So how we can tackle that? If mid square is causing the overflow, how we can tackle that? We can write it something like, if mid square is greater than x, then mid should be greater than x square mid. So let's try to submit it. Yeah, you see, it's submitted. So we can apply binary search to find the square root of x, and it's very simple. So hope you love the concept, hope you like this video. Then please do like, share and subscribe this channel, and please put your feedbacks in the comment. I'll be reading all those comments, and see you in the next video. Bye.